Okay, so we're finally getting to that base E that we're talking about. It is a number found by this gentleman over here, and his name is pronounced Euler, not Euler. And if you ever watch Big Bang Theory, they really refer to him quite often. And it surprises me that they still let it go as jokes because most people don't know who he was. But he was a god in Switzerland. In fact, at one time, their money had him on there. Not at the time the king and queen of Switzerland, but Euler. So he found a number. It actually had existed, but he had done the most work with it. And it's base E. And base E is 2.71828. Now, it is an irrational number, so it keeps going on forever and ever. Kind of like pi, not like, exactly like pi. Pi is 3.14, I think 15, and then I'm done with knowing the rest of it. Now, it's the summation. I'm just going to tell you really quick that this is a symbol you're going to learn later on in statistics. It means to sum up, and it's the sum of 1 over 1 n factorial, and that means it's like 1 over 1 plus another 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and if you add all those numbers together, you get 2.718. Now, I am not going to go into the history of E. It's kind of understand that it is a powerful number. I told you it's more powerful than pi. We use it in chemistry. We use it in biology. We use it definitely in finance. It is all over your money markets. And to find the history of why it is, we don't have that time in Algebra 2 to go into it. So it's kind of like I'm introducing you to the number. I'm going to show you how we use it. And then if you pursue economics or math later on in college, you will do a lot more research on it. So it is an exponential graph. It is y equals e to the x. And if you look on your calculator, you actually have a key dedicated right to base E. Here it is right there. Notice that log undoes 10 to the x, and natural log is what ln means, is e to the x. So that's what ln means. ln is natural log. Now you can see where the n and the l came from. So why wasn't it called NL? Well, because Euler is Swiss, and Swiss has a French background, and as you know, if you speak French, your adjectives come after your noun. So in France, they wouldn't say the White House, they would say the house white. So that's why it's ln. It's natural log moved around. It still holds the properties of an exponential graph. An exponential graph must go through the point 0, 1, because still any number raised to the 0 power should be 1, and any number raised to the first power should be itself, and that indeed, when I put 1 in there, I get 2.718. So just as logarithm means base 10, when we write log and then x, and if we do not write a base there, it's understood to be 10. When I write ln for natural logarithm, its base is understood to be e, even though we don't write it there. So for example, natural logarithm of the number e equals what? Well, the answer is 1. Because, remember, it's base e, and if I were to read this, and remember, if we were going to read this, natural logarithm of base e is read as, what is the exponent of e that gets us e? Well, the answer is 1. Likewise over here, remember, there is a base e. what is the exponent of E that gets us 1? Well, that answer is 0. And to check ourselves, if we do our little sheet where we roll the log, rewrite it as an exponent, e to the 0 does indeed get us 1. So now let's see if we can take the shortcuts over here. Natural logarithm of e to the 5th is what? Well, what is the exponent of e that gets us e to the 5th? Well, like bases, the answer is 5. Well, that's one way to look at it. You could have taken it the long way too, which is that exponents fall down in front. What is the exponent of e that gets me e? 1. 5 times 1 is 5. Hopefully, if you can take the shortcut that I started with, life would be better. So rewrite using logs. Now, just because I say log laws does not mean base 10, because we are working in base E. All right, so let's peck through it one by one. I'm announcing I'm going to use logarithms. I have this x cubed, which is getting divided, but since I'm working in exponents, then I'm going to be subtracting e squared. Now, I can't have exponents working in exponents, so that 3 drops down in front. Now here you can either take your shortcut, because this can be done. What is the exponent of e that gets me e squared? It's 2. Or you could just do the long way, drop the 2 down in front, then say what is the exponent of e that gets me e, which is 1. And when I rewrite this using my laws of exponents, that's what I get. So we're finally going to learn how to solve an equation without having to rely on Desmos. A hot liquid is cooling in a room whose temperature is constant. Okay, so that means we're decreasing. So when I do go to graph this, I should understand that it is decreasing. And its temperature can be modeled by this lovely long formula here. T is the temperature in Fahrenheit. Now, I always do it over here. I list my variables, so there is a quick reference to them, and is a function of the number of minutes M has been cooling. I don't know if later on they may ask me to change minutes into hours, or even temperature Fahrenheit into Celsius, so I kind of just keep it over there. What is the initial temperature of the liquid? Well, hopefully now we know how to take that shortcut. If you don't, remember, it means we're putting 0 in for minutes. 101 e to the negative 0.037, and then in for m, I'm putting 0, plus 67. All right, well, 0 times 0.37, that's 0. Anything to the 0 power is 1. Oh, there it is. That's my initial temperature. And you're right, I wanted my shortcut to be where I just take my A value and either add on or subtract any translation that's going on. So that means the initial temperature of the liquid was 168 degrees. What does T of 60 equal 83.7? Well, remember, this is M, which is minutes. Oh, so that just must mean this. After 60 minutes, the temperature of the liquid will be 83.7, and I can actually even make that more precise, degrees Fahrenheit. Now, you must say of the liquid because there are two temperatures going on here, the room temperature and the temperature of the liquid. How many minutes will it take for the liquid to reach a temperature of 110? Okay, so there is what we are talking about where we used to use Desmos back when we had exponents. But we want to know (101) times e to the negative 0.037. We want to know how many minutes it's going to take for this equation to hit the equation 110. Now, I always come over here to Desmos, and when I type the two equations into Desmos, I see that my answer is 23. So, okay, I've got that in the back of my head. So I know that m should be about 23. Okay, so let's start solving this thing. 101 e to the negative 0.037, and I don't know what m is, plus 67 equals 110. I'm going to just minus 67 from both sides. It gets me 101 e to the negative 0.037 m equals, what is that, 43. Now, I am going to divide by 101, but I am not going to take out my calculator, divide it out, and get an answer. A lot of you got into trouble on your last test by doing that. You keep rounding and rounding and rounding. You never round but once your final answer. This is an ugly number, but let's leave it as that. It is a rational number that we can deal with. So now, how do I get rid of this e? Well, to undo bases, because I need to get to their exponents, I do logarithms. And in this case, since this is base e, I'm going to undo them with base e logarithms, natural logarithms. So I know that that means that these cross off, and I get negative 0.037 m. Now, if you're like, hey, Mrs. Trulin, how does that cross off? Well, remember, what is the exponent of e that gets me e? 1. And this would fall down in front. So the quick step is to just cross that off, and then I'm left over here with the natural logarithm of 43 divided by 101. Well, my last step is to divide by negative 0.037. I'm going to divide this entity by negative 0.037. Let's come over here and type this all in. The natural logarithm of 43 divided by 101. That is getting divided by negative 0.037, and voila, 23 minutes.